All right. So today we will study linear quadratic regulator, and as part of this study, we would get well acquainted with Riccati equation. Both are very useful. Both are integral part of optimal control. A lot of other concepts are dependent. Just to give you a quick motivation, directly, you can use it almost as much as PID control. PID control is famous for practical work. There is I can say, deep reason for that, which we maybe will discuss later, a bit later in the course. But PID control is famous for practical work, especially for very simple systems like a motor, single motor, other stuff like that. It works really well. LQR is sort of colloquially famous as a lab instrument. If you want to test something in your code, in simulation, etc., doing it using LQR is one of those quickest ways people do it. So it is an important tool to have in your belt. Also, concepts like LQR, basically like a first step to understand concepts like Kalman filter, the whole field of optimal control that uses LMI, and so on and so forth. So in a sense, it is a stepping stone for a gigantic number of other methods. So it makes sense to try to understand it. Also, it goes slightly outside of the old school classical program in control theory. So, for example, in a typical textbook, they would not go into LQR if the textbook is trying to adhere to transfer function representation of the systems and to discuss control theory mostly from the transfer function representation approach. Because LQR is naturally a state space method. So, on the one hand, it means we, try to go beyond maybe it is a good thing. On the other hand, if you are going to self-study it, just know that it is typically like out of normal introductory courses on the control theory. Right. Now, let us try to understand what it is. Okay. So first of all, we need to get a new term, which basically is the same as what we already had, but we need the language. So if we describe a dynamics in this form, x dot equals to f of x and u. And notice, this is a system of first order differential equations. So we have a derivative on the left-hand side. We have everything that does not contain derivatives on the right-hand side. And so this is the first order differential equation. And it is in this special form where only the derivatives on the left-hand side. The form that is very familiar to us because of state space equations, right? Now, let us define this dynamics. And for this dynamics, we can describe a control policy, right? Control policy. That is a new term, control policy. And it is typically described in this way. U equals pi of x. And is there a question? No question, right? Okay. Sorry about it. So we define a control policy like this. Now, if you remember our definition of what control law is, you may well ask me what is the difference between control policy and control law. And I think the correct answer is there is no difference. It's exact same thing. It is exact same thing. Control policy and control law are the same. But there is a reason to use both terms. Control law is used in control theory when we describe basically like stuff that relates to control theoretic problems, such as stabilization of the plant of the robot, right? We derive simple things like error dynamics and so on and so forth. Now, control policy is used in the whole realm of optimal control. In the whole realm of optimal control. And even beyond that, in things like neural networks, where you want to have an agent that acts in the world, and so have a control, we describe actions of the agent also as control policy. Well, something of the sort. Notationally, there is maybe a little bit of confusion because we have u here and pi here, but that is actually the whole benefit of talking about it this way, right? So let me point out the benefits. U here is the same as u here. That is just a control input. So particular value that your control policy produces. Your control policy takes as input a state, like current state, current time, right? And produces as output this u, which you can then put into your system. Now, particular u is just a function of time, right? Or it's just a vector of values. Now, pi is a function. You can choose pi. You can also control policy. You can choose pi. You can choose it as something else, and it would determine all future control outputs, right? So the difference between those two is quite clear. One, you can talk about choosing a particular vector if you're talking about u. If you're talking about pi, you're going to talk about choosing all future controls, your whole policy about how to produce controls, right? If control policy was linear, it would have been the same as choosing k. So choosing pi would be the same as using k in u equals to kx control. If that is your controller, then choosing pi is the same as choosing k, control gain. But it doesn't have to be linear, right? So in general, it is, it covers more. All right, good. Now, we, in this part of the course, in this lecture, will concern ourselves with a new idea, and that is optimality, right? In terms of control, optimality refers to the idea that you can find such a control that is better than any other, all right? So far, we have been talking about stability. So control that actually allows us to work without blowing up, without state going towards infinity. Now, here in this lecture, we are talking about optimality. So choosing not just any control that allows us to not blow up, but the best control out of all possible ones. Okay? To be able to say that something is better than the other, you have to be able to measure both things. So if thing A, you want to say that is better than thing B, you have to be able to measure both. So somehow we need a function to evaluate how well our system performs under a given control law. And the way we do it is via cost function. Specifically, we would use additive cost function. Additive. the fact that it is additive would be useful in deriving almost everything else. But in a sense, it is very natural. Additive means you would have integral, and you would integrate from, let's say, 0 to infinity, some kind of function, right? You'll integrate. All right. Now, the way I describe it is this additive control function J is like this. So J is a function of initial conditions and control law, right? So there's a function of initial conditions and control law. What it does, it integrates from 0 to infinity certain instantaneous cost, but x here is x that is produced as a solution to differential equation f of x, x dot equals f of x, with this initial condition and this control law. So that's how this cost function works. Let me try to repeat it, but maybe I'll try to be like more tight about this. So your cost is just the sum of all instantaneous costs. This cost we evaluated on the trajectory. So we get a solution, let's say something like this. We, on each point of this trajectory, we compute G. We integrate G, and we get our J. Right? Initial conditions are important because different initial condition would produce you different cost, right? So the cost depends on where you start. If you start on the trajectory and your what do you call it, control law, your policy is able to drive you exactly along the trajectory in the way as we described, as the inverse dynamics allows you to do it, well, then your cost would presumably be zero. But obviously, if you start away from the trajectory, the same control policy would produce much worse outcome. All right. Okay. And this might be obvious, but hopefully we understand that those two completely define the solution of the system, right? So if you have like x dot equals f of x system, f of x u, then knowing initial conditions, knowing control law gives you solution. So your solution does not depend on anything else. All right. So that is the cost. That is the cost. The cost. Now we need to describe optimal cost. So lowest possible cost, right? We will describe it using the idea of infimum. I guess if you're more comfortable with thinking it as a mean, right? Just think about it as a mean, basically like minimizer, right? Over pi. Notice we minimize over pi. So this notation, when you write infimum or minimum, minimize, whatever else, argmin, any minimizer here, under it, you would write the variable which you are allowed to change to do minimization. So here we change pi. So notice we don't change u, we change pi. Of course, we could say over u of t, but that would be disingenuous, right? So in a sense, what we change here is specifically pi. So the law, how to relate current state and time to u, right? That's what we change. So our decision variable is a function. All right, all right. And what we are saying is lowest optimal cost is a cost that depends still on the initial condition. But now we chose the best possible policy. Now, optimal cost, you would find it when we find the best possible control policy. The best possible control policy will describe as pi star. So the optimal best possible cost is J star. Best possible policy is pi star. All right. So the star represents the best in this lecture. All right. Good. Now, with that, what we can do is we can formulate Hamilton-Jacobi-Bellman equation. That equation tells us the conditions for when a control policy is optimal. All right. So let us look at this condition. Let us look what it does. Well, this condition, it represents, it is written in this way, right? Where on the right-hand side, on the left, sorry, on the left, what we have is minimum over u. All right, minimum over u. Notice not pi, but this time u, right? Minimum over u over this expression here, which contains our instantaneous cost g plus partial derivative of the optimal cost with respect to x. So dj star dx times f of xu times f of xu. All right. And that's what we have here. That is the condition. It may look a little bit strange, but that is the condition for optimality. So it has to hold for any specific x that we chose. It has to always hold, right? Obviously, this u here we don't choose, right? The whole point of this condition is that the u here would have to do with policy. So it depends entirely on policy. While u agrees to the optimal policy, of course, this condition should hold. But x, on the other hand, we can choose, right? And this has to do, of course, x also has to agree to control policy and to initial conditions. But we are free to think of any initial conditions. Right? So x, in a sense, we can choose here. X we can choose. And notice here u is being used, like this very u, is being used to minimize this function, right? So the way you read this equation is not this formula should be equal to 0. What you read is the minimum of this formula with respect to the variable u has to be equal to 0. Right. And this automatically gives you the formula to find optimal control for a particular state. So your optimal control, u star, is just argmin of the same function. Just notational thing, right? Min gives you as output the minimum value of what you minimize. Argmin gives you as output the argument that provides the minimum, right? So min would give you minimum of this function. Argmin would give you the u that provided the minimum to that function. Right. At this point, you may ask why this equation, how did this equation come about? That is, as far as I know, that is not anywhere. Like it's very difficult to find proof for this equation. Let me see. We should have it at the end of the slides. So let me quickly look it up. Look it up. Yeah. So in case you wonder, you can find derivation here. You can find derivation here. Right. Okay. For now, we'll continue. If at the end of the class, if we have a little bit of time, I'll go with you through this last slide. All right. Now, our game from this point on would be to use this to apply it to linear systems. All right. That will be our game. So linear LTI dynamics, as you remember, looks like this. X dot equals to AX plus BU. Notice we don't have control output here. No Y equals C of X, C times X. The reason we don't have it is because we don't need it for this for LQR. So LQR, this whole like optimality thing, as you noticed, is a function of state, not the output. We could try to formulate all of this in terms of output, but we didn't. So output is irrelevant for this formulation. Now we need to choose our quadratic cost, and our quadratic cost, we can choose it as, for example, X transpose Q transpose X plus U transpose R U, where both of those variables, Q and R, are positive definite. At very least, R has to be strictly definite, positive definite. Q can be positive semi-definite. Do you remember what positive definiteness means? So tell me. Right, maybe you don't. So positive definite matrix is a matrix which is symmetric. Typical assumption that it is symmetric, and its eigenvalues are strictly positive. Semi-definite means some of the eigenvalues can be zero. We don't have to assume that it is symmetric. It depends on how you prefer your definitions. You don't have to assume that it is symmetric. If your definition comes from quadratic forms, maybe you remember positive definite quadratic forms, right? Positive definite quadratic form is such quadratic form that for any x quadratic form, you remember what it is, right? It's something like x transpose q, sorry, x transpose qx. Positive definite quadratic form is such quadratic form that it will be positive for any x. Well, semi-definite means at least non-negative, right? In this definition, Q doesn't have to be symmetric, right? But we typically assume that it is symmetric, and for our derivations, it is fine. So that's just it. Positive definite matrices tend to produce quadratic forms. Like they always produce quadratic forms which are strictly positive, semi-definite, positive, or non-negative. Also, the positive definite matrix is invertible. All right, good. Now, that said, giving this f of x, and so x dot equals f of x in this form, giving our instantaneous cost in this form, we can substitute to Hamilton-Jacobi equation. So Hamilton-Jacobi-Bellman equation, you notice instantaneous cost. There's a partial derivative of the optimal cost to go. and there's f of x here. All right. So what we have here is instantaneous cost. So this guy. What we have here is a partial derivative of the optimal cost times the f of x. So please. All right. All right. Now, there is a theorem that says that for linear time invariant systems, optimal cost to so optimal value of the cost would be a quadratic form, right? So it would come in this way, where S is a positive semi-definite matrix. Here it would be good to remember that J star was a function of initial conditions. And basically that's what it means here. So those x's, you can think of them under as initial conditions. But so theorem says, and let me go back to the slide. Theorem says that for linear systems, when you perform this operation, what you would get here is a quadratic form. So x times matrix times x, right? That's what you'll get. I'm not going to prove it, but let's just assume that it is true, right? So very interesting result. What it allows us to do, it allows us to compute this partial derivative. Now, here, when we're going to compute it, we'll have a little bit of a little bit of an issue, right? A little bit of an issue. If you compute it directly, if you just do it like this, you say, okay, this guy, let me compute partial derivative of this guy. You would likely produce me something like 2 times maybe s times x, right? Maybe that's what you would produce me. Or maybe 2 times x transpose s. Or maybe you would even produce me something like sx plus x transpose s. That would be very bad because that would be a column vector plus row vector, right? That's not good. So the correct answer is to do it like this. This is the partial derivative times a x bu, right? You notice this is a row vector times column vector. And here is the same thing, but transposed. So here's ax plus bu transposed times sx, right? And this may look a little bit strange. This may look a little bit strange. I think this may look a little bit strange, but and you know, maybe there is a way to teach this where just like here is a set of conditions, set of formulas when this occurs and so on. But to me personally, to remember this part, it is just like feels natural to go back to this equation here, right? This equation, and just see that this is essentially a full derivative, right? It is the same as saying dj dt, right? I'm you know, this is this is the mathematics where you need to be careful, and I'm not being very careful right now. So please take it as a grain of salt. But you can see what I mean, right? It is dj dx, and this f is dx dt, right? So in a sense, at the very least, I can say that it is, dot dot dot. This is equal to dj dx times dx dt, right? So something like a chain rule is being applied here, right? And then if this is how you see it, you can do the following in the next in here. What you can do is basically you can say, okay, my j if I want to find dj dt, right? This dot dot dot, as I said in the last equation. What I would have is how do I write it? Dx dt transposed times sx plus x transposed times s times dx dt. Right? That's what I would have. And so basically it's like x dot here or x dot here. So time derivative of this guy would be equal to x dot times sx plus s x s x dot, right? And now each of those x dot just becomes ax plus bu, right? And that's how you can remember. If you take derivative of this guy with respect to time, and you start by remembering that x is a function of time, so you replace x with x dot when you take derivative. S itself is not a function of time in our case. Then this step is very smooth, very easy to understand. All right, good. Good. Next, what we want to do is to simplify. How do we simplify? Well, first of all, we want to get everything that contains only x in the brackets. So this, as well as this gives us only elements that are quadratic in x. Also this, right? So this goes into the brackets. We also get everything that is semi-quadratic in x, right? So bilinear. So where you have both x and u. And r remains the same, right? Well, that is more or less it. Okay. Now next, we want to find partial derivatives with respect to u. So how do we do that? Well, partial derivative of this guy with respect to u would be, something like u 2u transpose r. Right? Partial derivative of this with respect to u of this whole thing will be 0, right? It doesn't have a partial derivative with respect to u. And partial derivatives of this with respect to u would be x transpose sp, and here it will be the same, but with this it will be the same. Now, why we find partial derivatives? Well, we still have this minimum, right? So we have to do something about it. You know that the function attains minimum at an extremum point, and the test for extreme or at the border of the optimal problem. But here we have no borders, no constraints, so just E extremum. And test for extremum is partial derivative equal to 0. So that's why we take partial derivatives. Now, it is possible that for you, the way I take those derivatives is unclear, right? Is unclear. Well, to take derivative of something like this, you can just do it by hand, and you would sort of understand what's going on, right? By hand, what I mean is like element by element. But in case, there is basically like a formula. So let's say d something. Let's say du transpose r transpose u, and derivative with respect to u, right? What would be the derivative here? Well, it is the same as, let me put it like this. It would be the same as derivative of this times this. I'm applying chain rule, right? Sorry, I'm applying the formula for derivative of a product, right? And here it would be the same as this times this. So, I hope you understand what I just did. I took this expression, then divided it, leaving in the brackets only the first part. The other part goes out of the bracket, and here I took this part out of the bracket and I left this part, right? Hopefully this is clear. Now, next, we can observe that like this is clearly one identity, right? So that's how we get this guy. But this is not completely clear. This is not completely clear. And basically, the way you do it is like this whole expression is confusing, is what I'm trying to say. This whole expression is confusing. Even like, like this, I'll let me put it in square brackets just so you notice. It is confusing. It's not a very good expression. Yeah. Basically, the correct answer here, I'm just giving you like the formula, is this guy transposed. That's the correct answer. That's the correct answer. So when you try to do something like this here, right? You try to take a derivative of a horizontal vector with respect to a vertical vector. Times stuff like this is whatever modifies this vector. The linear operator that acts on this vector. Well, you have to transpose this linear operator. That's what happens. You can find there's a whole table of such rules, and they're quite elaborate because like this is a relatively simple case. There are much more complicated cases. But yeah, so that is basically how you take this derivative. That is why derivative with respect to u of both of those cases will produce exact same result, because here u is not transposed, so you would get this part, and here u is transposed, so this will be transposed. Right? Okay. So here is the answer. That is the partial derivative. Obviously, those two would go away, right? And we can express u out of this equation. The way we do it is we multiply both equations by r. So we get, sorry. The first step is to transpose the equation. That would be a better way to go around it, I guess. So we first we transpose this equation. What we get is RU equal to minus B transpose SX. Notice that since S is a symmetric matrix, R is a symmetric matrix, you transpose them, but the transpose is equal to the original. So we don't keep transpose in front of them. And after that, you multiply both sides by R inverse, and that's how you get this equation. Now, notice we have been doing a little bit of mathematics, but what we achieved is optimal control. We already found something. So this equation 12 gives us the best possible control that LTI system can have under the cost that you chose. So depending on which cost you chose, this will be the best control for this cost. As simple as that. The only problem why you cannot apply this to your problems yet is you don't know how to find S. This cost to go square like matrix in the quadratic form. You remember? S is what defines J star, the best possible cost, and you don't know how to find it. But other than that, you could already apply it. So it's pretty good. And notice we also proved that the best possible control policy is actually linear. It is just this minus kx, you know. So this is the control again. It's quite impressive, really quite impressive. All right. Now, all the by the way, if you use this control again, that is what is called LQR. So if you use this linear control policy and your gain is found this way, then it is LQR. What you're doing is a linear quadratic regulator. It is called linear because we consider linear systems, quadratic because quadratic cost, and regulator is just the older word for controller. In Russian textbooks, by the way, we still call it a regulator. Yeah. So a regulator is just older terminology for controller. LQR. So that is it for what LQR is. All we need to do is to find S. Like we still don't know how to do it. Let's next slide. All right, let's see how to find S. So the way we will do it is, let me go back. We will substitute here, instead of U, the optimal control that we found, right? So instead of U, in all of those cases, we will substitute what we found, right? So we put U here and here. This is U in front of R here. We substitute U here and we substitute U here. So for like X, S, B, U, now it is X, S, B, and all of this stuff, right? So that's what we did. Next, we can simplify. Some stuff is very easy to simplify, like this R times R inverse goes away. Okay. Next, what we notice is that after we simplify that, we have 1, 2, and 3 equations which are exactly the same. 3 parts of this equation is exactly the same. And 2 of them have minus sign in front of them. 1 has a plus sign. Because of that, this equation here would have a 1 minus sign. So basically, you could say that this cancels with this, you know, something like this. All right. And what we got here is basically a quadratic form that has to be equal to 0 for all x. And this is only possible if the matrix of this quadratic form. So if this matrix here would be always equal to 0. And this is what we have here. And that is called algebraic Riccati equation. That is called algebraic Riccati equation. Now, algebraic Riccati equation is the backbone of LQR. It is used while in a great number of other derivations. But for us, what is important is we solve algebraic Riccati equation to find S. S is unknown in this equation. And this equation is quadratic with respect to S. Right? So you cannot solve it using algebra, linear algebra. But there are, what is good for us, there are solvers. So there are programmatic tools which would just do it for us. We don't have to do it by hand. Right, algebraic Riccati equation. Good. So the way we would solve it is like this. We'll just take, for example, MATLAB function, LQR. We give it matrices A, B, Q, R. And we get as output optimal gain, optimal cost to go function, and even eigenvalues of the system. In Python, there is a SciPy library with a linalg, where it has a method solve continuous array, algebraic Riccati equation array. And it gives us A, B, Q, R as inputs. So exactly the same. Notice this guy only gives you S. So it gives us the optimal cost to go. So from that, you have to compute K yourself. That's it. That's it. Now, let us sit for just like half a minute. If you have any questions. No? You could realistically ask me why exactly we spend so much time on derivations, right? It would be a reasonable question. Why exactly we need to go from here? And if you learn the field, you would find that very rarely people go from here. Like very rarely we start this far away. Like this is definition, so I guess you would find it somewhere. But like Hamilton, Jacobi, Bellman, yeah, like we start quite far away, and then we go through all of those steps, all of this, just to find two formulas that we actually need. Basically, this one formula, right? That is the one formula that we are going to need. And the fact that you can solve this equation 16 using two methods. So why spend so much time? Well, there is actually a reason. First of all, here we assumed that A and B are constants. What you would find if you are going to do research is that often it is a bad assumption. Often it is better to assume that they are changing with time. For example, when you follow a trajectory, you can assume that your A and B matrices are changing on this trajectory. That has to do with linearization techniques. Now, if they are time variant, so they are functions of time, then when you take this partial derivative here, what you would find is that it should be different. It should be different. Like the answer wouldn't be like this, differentiated in this with respect to time. There will be additional term, namely s dot. So you'd have additional term here, s dot, right? But the rest of the derivation will be exactly the same. So you'll be able to derive all of this exactly the same. And as a result, you'll get what we call a differential Riccati equation. So this guy would be different in one term. There will be minus s dot here, if I remember right. And you would get a different method called TV-LQR, time variant linear quadratic calculator. Essentially, by understanding this process, you not only understand the one method, LQR, you understand the whole range of methods. You can do LQR on affine systems. Derivation is roughly speaking the same. You can do LQR for different costs. Like here is a pure quadratic cost. You can add linear elements to this cost. It would work. So if you understand the derivation, you can, because there's very simple derivation. At the end of the day, it is just substitute, take partial derivatives, take full derivatives, substitute back, get a differential equations, and it is not complicated. So that's fine. But all right, even in this lecture, we will try to do a little bit of this by showing you how fast you can derive the same for discrete LQR. Now, before we do that, let me point out a few downsides and upsides of two methods. So you remember pole placement? You studied it on practice. Basically, a method where you find such k that your poles, so your eigenvalues, in the correct have correct values. Right? Now, pole placement has advantages. So it allows you to design precisely how fast your control error goes to zero. So if you want your control error to go very fast, you can do it by give it big negative eigenvalue. You want to have less oscillations. Like, for example, you don't want to see this behavior. You want to see this behavior. Easy. Give it a real eigenvalues. Request no imaginary parts. Now, there are downsides to pole placement. If you ask for something bad, so something that the system has trouble producing, it would require unreasonably high control gains, right? So it is very easy to ask bad things using pole placement. You would ask something, and the system can either barely produce it or not produce it at all, and you'll get error. For big systems, knowing what to ask for becomes just a huge problem. Imagine you have a system with 30 states. How would you go about trying to imagine what is a good eigenvalue to ask for? It's very difficult. It works well for motors and other small systems. Doesn't work for a gigantic system. And let me just remind you, quadrotor, you would think it is a very simple robot, right? Quadrotor. It has 6 degrees of freedom, right? 3 translations, 3 rotations. It means it has 12 states. So already you would have to ask about 12 eigenvalues. That is more than what you want. Like, do you want to guess what are 12 eigenvalues of quadrotor? Of course, it's not like very difficult, but still. All right. Now about LQR. What is good? It is very easy to produce reasonable control gains. So LQR, naturally, since you ask only for the cost, you don't ask for specific performance, it is very easy for it to produce reasonable gains. Like, ask for reasonable cost, it will produce reasonable gains. And you don't need to know anything about the system. All you need is to just guess what cost suits you, all right? everything else would be done by the algorithm. The downsides, uh, if your system prefers to decay slowly, it is very likely that LQR will allow it to do it. Same with oscillations. It's not going to fight against them. So it is polar opposite of pole placement. This guy, very easy to ask for bad things, but you can ask for exact performance if you want. Here, very easy to ask for good things, but performance may suffer. At the end of the day, it is good to have both because sometimes, like once in 2 years, you would actually need exact performance. Most of the time, what you would need is some kind of stabilizing control that you can uh, produce by the, um, flick of a finger, right? And not only easy to produce, but also easy to tune. For LQR, what you tune is cost. So those two matrices, right? Q and R, you tune them. By choosing Q and R, you get different LQR gains. And remember, those are matrices. But in practice, often what people do is they'll say, okay, Q is equal to, let's say, 10 times identity matrix. R, let's say, is equal to 1 times identity matrix, or let's say like 2 times identity matrix. That is very typical. Of course, those identity matrices would be different, right? Different in size. But yeah, still identity matrices. And this way, you just get two parameters that you have to play with. The coefficient in front of position cost, coefficient in front of control cost. Of course, in terms of like real life performance, this is not good because for a lot of robots, etc., different states would have to be treated differently. You cannot just treat them like this. But it's very easy to go next step and do diagonal matrices with different elements of diagonal and so on and so forth. So it is still very versatile, right? And for the first test, you can just do this, and you would already see your stable controller. All right. Okay. Now, next, let us do the same, but for discrete dynamics. And it should hopefully be much faster, much easier. So here is our discrete dynamics LQR, sorry, LTI. Here is our discrete dynamics cost. Notice that the cost is now a sum from 0 to n, right? In this case, decide to put it to n, right? Of again quadratic cost with respect to q, with respect to x, and u, right? Same q and r matrices. Now we can define cost to go, right? For given initial conditions. So we can define cost to go like this. Notice now it is the same as optimal cost, but now we minimize with respect to u, right? We minimize with respect to u. Now, sorry. Sorry, one moment. Just 1 second. Sorry. All right. Now we're back. So what we find here is a cost to go for a particular state, right? So basically, you can say we have like a trajectory. We can x of I, which depends on f of x as before, depends on the control law, and we find the cost to go from time 0 to n. Right. Now what we can do next is given optimal trajectory that starts from x0, follows some optimal control policy, we find like a sequence of states, right? First state, next state, next state, like steps on the trajectory. For each of those, we can find optimal cost as well. So here is conceptually it is like this, right? We have a whole trajectory. Let me draw it, I guess, maybe like this. I apologize for a shaky line. Right, we have a whole trajectory. Now, if we start from here, we have to compute the cost associated with the whole rest of the trajectory, right? And indeed, it have to be optimal. Like if we trying to find optimal cost to go, this would have to be optimal cost. Now, after we made a single step, let me show the step like this. We make a single step on the trajectory. We are now here, right? So we can compute optimal cost from this point as well, right? And it will be something like this. It will be smaller. I'm here visualizing cost as a distance, but that is just a sort of like visual. It's not meant literally, right? Although you can always, of course, put a cost as a square, like a distance to the goal. You can do it. All right. So what we have here is illustration of how when you follow your optimal trajectory, on each next state, your optimal cost will be lower than on the previous state, right? If you start already at the goal, your optimal cost will be 0. But goal is one of the points on this trajectory. So the idea is that as you examine states that are closer and closer on this trajectory to the goal, your optimal cost to go have to be smaller and smaller and smaller, right? Okay. Good. So for each of the steps on this trajectory, it starts from k equal I equal k. Sorry, there's a mishap here. And we go from k to n. We compute this like left segments of this trajectory, and we get a smaller optimal cost to go. Now it is still a quadratic form, same as before. So the optimal cost would still be quadratic function of x on each step. All right, good. Now just like changing variables so we don't have indices. We call, let's say, x0 as z. We call u0 as w. W, I can call it w, right? We can write cost to go as, so the cost to go at point 0 would be a what we obtain by minimizing over control u, right? In this case, w, over this instantaneous cost. So that is instantaneous cost at the first step, plus the optimal cost to go starting from the next step. So if we know optimal cost to go for the next step, to compute optimal cost to go now, all we need to do is just minimize over our single control, like u0, right? In this case, w. And that's how we find optimal cost. So it is a difference between this approach and what we saw previously is that here it is not a question of partial derivatives, minimizers over continuous variables. Here it is a question of, on this last step, we want to optimize and our what is available to us is instantaneous cost plus optimal previous optimal cost to go. Yeah. Right. And notice that previous cost to go obviously would also itself will be a function of x, so it's a function of where it starts. So it's not just it's not fixed, right? It's not fixed. It is like you can see it as as a quadratic function. Okay, so this is called Bellman equation. You would probably see it in any course on like artificial intelligence, neural networks. If you're going to study neural networks that are not trained on data, but have to sort of like acquire data while training. So a lot of those. All right. Now with that, we can now try to apply it. I think it will become much more clear when we put it to use. So our cost to go at the moment 0 looks like this. Cost to go at the moment 1 looks like this, right? So we know at the moment 0, we can write it as z times p0 times z is equal to minimum over w of, this is our instantaneous cost. Those two guys are just our x1, right? That's how x1 looks in this notation. And this is p1. Now, notice that now it becomes much more clear what this v1 component here was. It's just a way to relate what happens next to what is happening here. And the whole idea hinges on the fact that we have P1 as optimal sort of like evaluator of the optimal cost to go for the next step. And we are computing the same thing for the current step. All right. Now let us take partial derivative with respect to W of this whole expression. We'll do it a little bit faster, right? But what we notice is this would give us, well, yeah, let me use, this guy would become this. Here, what we'll see is this whole expression times this. So where does it come from? This guy is from here. This guy is from here, right? When we take derivative with respect to W, we would have P1 times W. P1 times, so with respect to W, we have P1 times B. And in this case, taking, since it is a product of derivative of a product, we have this unchanged. And when we take derivative with respect to this variable, W transposed, it will be exact same, but transposed. And transpose times transpose will negate itself, and we would get the exact same expression. For symmetric quadratic forms like this, it is always resulting in same expression, whether you take derivative of omega or W transpose. So that's how we get this guy. All right. So this is what we would get by taking partial derivative. We cancel the 2 here. We transpose it. So after transposing, we get this becomes this, right? This becomes this. And finally, the rest is here. All right. I'll not dwell on mathematics. I think it's quite clear what we're doing. Now, from this expression, what we can do is we can find how W is related to Z. So we collect W on the left-hand side, Z on the right-hand side, and we find that W is equal to this whole expression inverted times this. Right? Well, it's a big chunky expression, right? And this was done for the first iteration. So we went from the cost to go at point 0 to the cost to go at the point 1. What we have here is the expression for in the general case. So your U sub I depends in this form on the X sub I. And it is exactly the same as here. It's just that here it was U sub 0, depending on X sub 0. Now it is U sub I, depending on X sub I. So we have P sub I plus 1 instead of P1. That's it. Yeah. This way, I apologize for W and Z instead of X0 and U0, but I thought it would be very confusing if I used derivative with respect to U0 and so on. So I avoided it. My apologies if it made it confusing. All right. Now, last step, I will just quickly go through it. I understand that this doesn't look pretty. The point is, it's not complicated. That's why I'm giving it to you. So we can define two variables, m and n, to simplify a little bit. And then our expression for u will become minus m times n times x, right? We have to substitute u into all of those positions here in this equation. All right, let's do it. So we get here, we substitute it in front of r. Here we substitute it in front of b. And that's it. Next, we observe that, let's clear all of this. Basically, what you observe here is that you have these guys, so like n transpose m. These guys surround two expressions, this expression and this expression, right? So if we put it out of the brackets, it was n transpose m, we would get the same expression here, but surrounded by n transpose m on both sides. But notice there is an inverse. So basically, this expression is m inverse. So since this is m inverse, it would cancel with one of the m's, right? And when it cancels with one of the m's, it becomes the same exact as those two expressions. And with a plus sign, those have minus sign, so one of them cancels. And that's how we get this last one. So the process is exactly the same as previous, just the numbers are different. But you would have same like big guy with three exact same expressions which cancel each other. That's all. And with that, what we have is a formula for discrete LQR. Now, with discrete LQR, there is that is all. That is the formula, right? That's the formula. With discrete LQR, you have a little bit of a difference between normal LQR and discrete LQR. So the way it works is like this. For discrete LQR, you want to first find all those P, right? And you can see that it is done in the form of backpropagation. So if you know final P, you can find previous P. So what people often do is they set the final P and they try to find all the previous ones from there, right? So, that is possible. Or there is a alternative, quite interesting way. Some people do discrete recur is by assuming that it should even teach you this kind of stuff. By assuming that the all those p across all steps should be the same, they run this algorithm until it converges to the same p. So that's another way. Is another way to do it, right? But regardless of how you would do it, you can see the formulas are quite clear. And also, of course, you would have automatic tools to do it. All right. Hopefully, what you have seen from this second part is not only that, okay, there exists another bunch of mathematics that actually covers this whole thing, but also hopefully you have seen that using something like Bellman equation, etc., is not so complicated in linear control. A little bit complicated, but not very complicated, right? Expressions are big, but conceptually it's simple enough. Right, that is it from me. We don't have time for anything extra. So try to look through this derivation, try to understand, especially, I would encourage you to understand at least the continuous part. I can almost guarantee that some of you would see it on the exam. So trying to understand it. If something is unclear, something is mysterious, I will be happy to discuss it with you on the next lecture, before the lecture, after the lecture, whichever way. Is important part of the course. I think it should be a last mathematics heavy lecture. All other lectures should be, unless I'm mistaken, simpler. So it makes good sense to give it a little bit of time. Right. I think with that we can stop the recording, and if you have questions, I'll answer them.